So this is your guys' last class of the week. And then you guys are done for the week, huh?
I think what you meant to say is this is our last class for real.
Oh, it is, isn't it? Oh, we should have had party hats and stuff. It is your last class for real. Oh my goodness. How are you guys feeling about that?
Really looking forward to summer.
Oh, okay.
Yeah.
Great. I remember my last class and I was like, it's kind of like the end of an era. Like I had been in school for so many years that I was like, this is going to be weird. But the money is good. So you guys will appreciate making money. I could buy a
And
car.
spending it.
Well, yes. So take advantage if you don't have kids and stuff, take advantage of all this disposable income. So yeah, spend your money. Have a good time. Well, I guess you'll have to wait till COVID's over. I get my COVID shot today.
Aren't you lucky?
I know, but you know what this means? It just means I'm old. So they're letting us Gen Xers go get the shots now because no one else wanted them. So I guess we're getting the yucky one, but I'll take it. I'm teaching field school starting next weekend. No, not yeah. Next weekend I start teaching field school, and then we're doing a materials school for the second year students. So true enough. You're young, Pavel. I'm not. I don't know if my body would fight it.
The problem is if we do get it, just because we fight it doesn't mean we can't spread it to other people who then can't fight it. That's the problem.
Yes. That is true. Well, you guys are young and healthy. I'm jealous. I wish I was your guys' age again. The energy and the vitality that you guys have. I remember those days fondly. Okay, we don't have many participants, but you know, people may be just done. I'll give everyone one more minute and then we're just going to start because we have a lot to cover today.
Elena?
Yes.
Hey, good morning.
Good morning.
Did you say last week that test 4 is going to be harder than test 3?
No, because I'm going to make some modifications. So test 4 will have some theory from frozen soil. So test 4 will be out of 21. So test 4 will have 2 marks for theory on frozen soils. I will give you 6 questions ahead of time. So I'll give them to you at the end of this week. And your test will have one of those 6 questions on it. So if you prepare ahead of time, say in a Word document, when it comes to the test, you would just have to copy and paste your answer. Same with, there'll be 1 question on a course reflection. So there'll be 2 questions. You'll get one of those 2 questions, and it will be a course reflection question. And I'll tell you what that question is ahead of time. And so you can just prepare 2 answers, and one of them will be on your test. There'll be one very straightforward question, which will be identical to the example problem. And there'll be one where you utilize the theory as well, which is very similar to an example problem. I wouldn't say it's identical word for word as one of your example problems, but it's applying the same theory. So I think test 3 people found difficult because there was a lot of theory and a lot of multiple choice. So there won't be the same theory requirements.
Okay, thanks.
Yep. Okay, let's just start. Okay, well, good morning. I guess this is your very last course lecture at Red River. I was going to say for GM2, but I guess it is your very last course lecture for your program. So congratulations, you've made it. You guys must be very ecstatic. You've worked very hard this year, especially considering these extenuating circumstances. You guys have excelled, so be proud of yourselves. Today's lecture, we're going to focus on retaining wall design. So it will be probably a 2.5-hour lecture, maybe approaching 3 hours. And then next week, I'm open, or later this week, if you guys would like another session on retaining walls, I'm open to doing an hour-long session as well. So retaining walls, there's 3 PowerPoint presentations associated with it. The first PowerPoint presentation just provides an overview of the different types of retaining wall structures, and it provides figures, sort of giving you an indication of what these retaining structures would look like if you were to see them in the field. So there's examples of gravity retaining walls, mechanically stabilized earth retaining walls, cantilever retaining walls, soldier piles, modular walls. So there's just a plethora of different types of retaining wall structures. So that's what the first PowerPoint presentation is. So just take a read through that. It shouldn't take you more than about 15 minutes at the most to read through that. I'll go over PowerPoint presentation 2 or 12B and 12C today with you. So to understand the design of retaining walls and potential causes of failures of those retaining wall structures, you first need to understand the horizontal stresses of a soil acting on a vertical surface, such as a retaining wall. So the first hour and a half or so, I'm going to go over with you guys how you do the calculations for those horizontal stresses. I'm going to share my screen. So if anyone has any questions while I'm going over the PowerPoint slides, don't hesitate to unmute yourself and just ask the question, or you can ask it in the group chat. So horizontal stresses in a soil, you'll see that horizontal stresses in a soil always increase linearly with depth. And that's the same with vertical stresses in a soil. So if you look at this horizontal stress distribution, you'll see that your horizontal stresses are always increasing linearly with depth. Horizontal stresses, when we're calculating them, we always use our effective vertical stress when we're calculating what our horizontal stress is. So if we think of retaining walls in Manitoba, it's not too often that we conduct retaining wall design. So we might design a retaining wall if we were going to do an excavation to install piled foundations for a high-rise structure or for a structure in Manitoba. You might see an excavation, it'll probably be over 5 feet deep. It could be probably down to 8 or 9 feet deep. And then you'll see usually a soldier pile retaining wall structure. And then you can have equipment and crew in there installing your deep foundation. I think the rapid transit line in South Winnipeg, they used a modular retaining wall structure for one of the embankment approaches. So there's another example. If you work in provinces such as BC and Alberta, retaining wall design is quite common. They use them on highways, they use them for residential and commercial developments because they're building developments on hill slopes and highways on hill slopes, where in Manitoba it's quite flat, so we don't have the same type of geography and topography. So that's a brief overview of retaining walls. So again, as I mentioned, your horizontal stresses are, your horizontal earth pressures are always increase linearly with depth. So your horizontal stress distribution increases linearly with depth, and we always use effective stresses to calculate your horizontal stresses. There's 3 possible cases that may result, in retaining wall design, and they're dependent on the potential direction of your soil movement. So if we think of a soil particle below the ground surface, that soil particle, if you think of it, it has a vertical stress, which is its overburden stress, and it also has a horizontal stress. We previously covered this in Module 4. That soil particle, when it's at rest, it's not going to experience any movement. So the way we calculate our horizontal stress for that soil particle is we use our K0 value, which is our coefficient of earth pressure at rest, because that soil particle is not going to move. There's no external pressure being applied to it that would cause that soil particle to move. There is overburden pressure, but that overburden pressure isn't causing that soil particle to move. The next possible case would be an active case. So if my hand right here is my retaining wall, this retaining wall will have a soil mass behind it. So this soil mass behind the retaining wall, imagine this, my pencil represents part of the soil mass. This soil mass is trying to push this retaining wall downwards or outwards. So there's a force being applied to that retaining wall that's trying to cause that retaining wall to slide or to overturn. So that there's a force being pushing against that retaining wall and it's moving it outwards. So that would represent your active case. So there's soil pushing against the retaining wall and moving it outwards. Your passive case, again, imagine if my arm is your retaining wall, you have your soil mass, say, to the right of my arm. And on the left-hand side of my arm, can you see the pencil? I see the pencil. Hopefully you can see it. On the left-hand side of the retaining wall, there's a force being applied to the right. And that force being applied to the right is either from a tieback rod or an anchor or a brace. And it's pushing against the retaining wall and the soil is moving inwards. So there's an external force being applied to that retaining wall that's pushing that retaining wall inwards. So instead of being pushed outwards, in your passive case, it's being pushed inwards. Okay, I'm going to pause there. I want you guys to ask any questions if you have it on the at-rest case, the active case, or the passive case. No? Okay, well, with your active case, oh, sorry, go ahead. There's a question.
For the number 1 at-rest case, was there supposed to be a pile there? Like, I don't see anything.
No, at-rest case is just when you're not doing retaining wall design. So with retaining wall design, you never use your at-rest case. You would only ever calculate what your horizontal stress would be for a soil particle that's below the ground surface, but there's no retaining wall being constructed. You only ever use your active or your passive case for retaining wall design. You would never use your at-rest case.
I have a question.
Sure.
You mentioned about the anchors. So those anchors you usually using when it's clay soil, or it doesn't matter?
It doesn't matter. You usually use it to provide additional support. So it could be in sand, it could be in clay. If you need additional support, you would use a tieback anchor. So those tieback anchors are used to resist the overturning of that retaining wall structure. So there will be a soil mass behind that retaining wall structure. If that soil mass is going to apply a large enough force that it would cause the retaining wall to sort of move in an outwards direction and overturn or slide, then you would use a tieback rod or a tieback anchor. So it's like independent of your soil type, it's more dependent on the total force that's being applied against that retaining wall structure.
I've got a question.
Sure.
So all of these cases are for a pile that is not moving. It's just dependent on where the force is being applied, or is this assuming they're moving?
You design your pile so that your pile doesn't move, but there's different scenarios in which you have to analyze so that you can ensure that your pile is not moving. So we would do something like we would do our factor of safety calculations and we would design our tieback rods or our tieback anchors so that the pile doesn't move. Or we would design sort of the configuration of our cantilever sheet pile, of our cantilever retaining wall structure or our gravity retaining structure so that it doesn't move. So it depends how it's installed and it depends on the shape of the retaining structure. So you use your active and your passive forces, but you're designing your retaining wall structure so that it doesn't move. So we never use K naught in our designing of retaining wall structures. We only ever use K, our active force or our passive force.
Okay. So depending on where the force is being applied, we use whichever one of those.
Yes.
Type thing?
So if your force is being, so if this is my retaining wall structure, and so this will represent, so this green pen represents the
Yeah.
left-hand side of the retaining wall. There's no soil on this left-hand side of the retaining wall. The soil is only ever on the right-hand side of the retaining wall where my pencil is. So if you're in an area where there's no soil on the left-hand side of your retaining wall structure and there's a force being applied, it would be from a tieback anchor or from a brace or a different type of rod or an anchor, then that is your passive force that's being applied because there's a force being pushed against your retaining wall, whereas the soil, which is represented by my pencil, is the force that's trying to push this structure over.
Okay, so we use both of these forces in the calculation.
It depends, again, on installation. You always use active, and passive is depending on what type of structure you have.
Cool. Sounds good. Thanks.
Okay. So if we think of our active case, so in the case of when we have an active case, our Ka value, so our coefficient of active earth pressure, or our active earth pressure coefficient, is always less than our K naught value. So our horizontal stress associated with an active case is always less than the horizontal stress associated with an at-rest scenario. Whereas with our passive case, our Kp value is always greater than our K naught value. So the horizontal stress or horizontal force associated with the passive case is always greater than your at-rest scenario. Okay. We're not gonna, I think I sort of went over that. So this again is the same scenario that I was trying to illustrate with my green pen and my pencil. This is just a schematic showing what is your at-rest case. So your at-rest case is that your retaining wall structure isn't moving. So if you imagine that this is my retaining wall structure and I have a hand, I'm applying a force to that retaining wall structure, or a horizontal force is being applied to that retaining wall structure, but my retaining wall structure isn't moving, so it's at rest. If we, I think I'll come back to this. So if we look at our active case, again, it was the same scenario where my hand represents the retaining wall structure. And imagine I had my other hand was applying a force to the left-hand side of the retaining wall structure. If I was to decrease the pressure that I'm applying to this side of my retaining wall structure and sort of release my hand a bit, relax my hand a bit, then this retaining wall structure is able to move outwards, downwards, and outwards because I'm applying less force. So that's sort of your active case. And then your passive case would be the opposite of that, where if this is my hand, I have to apply additional force or additional pressure to this retaining wall structure to cause that retaining wall structure to move upwards. So it's moving in an upwards direction. So if we think about calculating horizontal stresses, so think back to Module 4. When we reviewed Module 4, we talked about drawing our vertical stress profile, our pore water pressure profile, and our effective stress profile. So those are coming back to haunt you because your horizontal stress profile will be identical. While the process behind it is the same as your effective stress profile. So to determine your vertical stress profile, you simply do these calculations. Gamma bulk, and this is if you don't have any pore water pressure. If you had pore water pressure at the top of your retaining wall structure, then gamma bulk would be replaced by gamma sat minus 9.81, or gamma buoyant times depth. So in this scenario, we don't have any water at the top of our retaining wall structure. So your vertical stress is simply equal to gamma bulk times depth. And in this scenario right here, your depth represents the height of the retaining wall structure. So if you look at your total vertical stress at the base of this retaining wall structure, your vertical stress, which in this case, your total stress is the same as your effective stress because you don't have any pore water pressure. So we'll say that your effective stress is equal to gamma bulk times H for your vertical stress. So if we look at our horizontal stress is simply equal to our vertical or our effective vertical stress times our K value. So it could be either Ka or Kp plus, in this scenario, it would be gamma W times H. Because we don't have any pore water pressure in this scenario, gamma W is equal to 0. So this part of the equation would go to 0. So our horizontal stress at the base of this retaining wall is simply equal to K naught, or it would be a Ka time or Kp times gamma bulk times H. So that is how we would calculate what our horizontal stress is at the base of the retaining wall. So I'm going to pause there because this is an important concept. Does everyone see the correlation between calculating your effective vertical stress and your effective horizontal stress at the base of the retaining wall, or your total horizontal stress, sorry, at the base of the retaining wall?
Question about the saturated unit weight. So probably we may have some questions on the test where we need to calculate that as well, right? Based on the
Yeah.
density or, okay.
I'm not going to give you density. I would just give you gamma sat, but we'll go through lots of examples today where we look at scenarios where there's no pore water pressure associated with our retaining wall structure and where there is pore water pressure associated with our retaining wall structure. So we'll go through a wide variety of examples today. So if we look at this slide here where it's talking about force due to soil at rest. So as I mentioned, we can calculate our total horizontal stress at the base of the sheet pile wall. And in this scenario, we'll assume our sigma H is equal to, in this case, we're looking at the at rest scenario, but say it was the active case. It would be sigma H is equal to Ka times gamma times H. And this represents your total horizontal stress at the base of the sheet pile wall. So this represents the width of your triangle. So if we look at the length of our triangle, so we'll say that this is the length of our triangle. The length of our triangle is the same dimension as the height of the retaining wall structure. So we know what the horizontal stress is at the base of the retaining wall structure. If we want to calculate the force, this simply is equal to the area of our stress distribution. So you'll see our stress distribution is triangular in shape. So our force is equal to 1/2 times base times height, because this represents the area of a triangle. If we know that the base of our triangle is equal to K naught times, or Ka times gamma times H, we know the height of our triangle is H, and then we multiply that by 1/2. We can calculate what our force is that's acting on the retaining wall structure by using this formula here. PA is equal to 1/2 times Ka times gamma times H squared. And then you guys all remember back to statics, where if you look at the centroid of a triangle, the centroid of that triangle, when it's acting in a horizontal direction, is 1/3 times H. So you would know that this horizontal force is acting at a location of 1/3 times the height of your sheet, or of your retaining wall. Anyone have any questions about how we determined what the base of the triangle is, so how we calculated the total horizontal stress, or how we're calculating the force associated with that retaining wall? So just remember, your calculated force does represent a force per meter width, and we'll show that when we go through an example problem. Is this totally new, a kind of an abstract concept, or does it sort of make sense based on what we did in Module 4?
It makes
Well,
sense.
we took uniform loads in statics as well, so it's very similar, just calculating different things.
Oh, okay, good. Phew. Okay, I'm going to go over an example problem. You guys are probably better at this than I am then. Okay, I'm going to stop sharing this. I'm going to go over an example problem. So today is going to be a day of many example problems. Also, I have prepared videos, so there should be videos of each of the example problems for this unit. So those will be on Learn as well. Yeah. Okay, why is this not going? There we go. It's going to be like, of course, on our last day, the IP vote decides to no longer work. Okay. Okay, example problem 12.1. So with example problem 12.1, it says that we have a dry sand behind a retaining wall structure, and it's supported by a 3.5 meter high wall. And it's asking for what is the lateral or the horizontal stress acting at the base of the wall for an at-rest scenario, an active case, a passive case, and then it gives you your different coefficients of earth pressure. So your K0 value is equal to 0.43, your Ka value is equal to 0.27, and your Kp value is equal to 3.7. So you'll see here, your Ka is less than your K0, and your Kp is greater than your K0. So if we look at this example problem here, this is the at-rest case scenario. So I've drawn a retaining wall structure, and you guys know by now that I'm a horrible artist. So this is my retaining wall structure. It's 3.5 meters high, and I've drawn my horizontal stress distribution associated with this retaining wall structure. And you'll see that my horizontal stress distribution is increasing linearly with depth. So if I want to know what the horizontal stress is acting at the base of this retaining wall structure for an at-rest case, my sigma h, which is my total horizontal stress, because it's dry sand, so that means that there's no water, is equal to K0 times gamma times H. So I know in this scenario, my K0 is equal to 0.43 that was given in the problem. I know the dry sand has a unit weight of 18 kilonewtons per meter cubed. And I know the height of my retaining wall is 3.5 meters. So I can go through and plug and chug and figure out that the total horizontal stress at the base of my retaining wall structure is equal to 27.1 kPa. If I want to calculate what my total horizontal force that's acting on this wall per meter of wall, I simply use this formula here. So P0 is equal to 1/2 times K0 times gamma times H squared. The problem has given me K0. I know what gamma is, and I know what the height of my sheet pile wall is. So I can just plug these parameters into the formula, and I can calculate that my total horizontal force for the at-rest scenario is 47.4 kilonewtons per meter. So I know what my total horizontal force is. And then I know that my horizontal stress distribution for this scenario is triangular. And because my horizontal stress distribution is triangular, to calculate the centroid of that triangle is simply equal to h over 3. So I know that my total horizontal force is 47.4 kilonewtons per meter, and it acts at a distance of h over 3 from the base of the retaining wall structure. So h over 3 in this scenario is 1.17 meters. So I know this total horizontal force is acting at a distance of 1.17 meters from the base of the retaining wall structure. I'm going to pause there to see if anyone has any questions for the at-rest scenario.
So did you just not do the passive on here?
Yeah, I just didn't do it on here. It's the exact same process. So if you went through and you were to calculate, and I'll go through that after Kelly, after I work through the active one.
Okay.
So the same process as what we did for the at-rest scenario would apply for the active case. So here I've calculated my horizontal stress. I've drawn out my horizontal stress profile for the active case scenario. It's exactly the same as what the horizontal stress distribution looked like for the at-rest scenario. So I calculated my horizontal stress at the base of the retaining wall structure for the active case. So I know in this scenario, my sigma h is equal to Ka, so sigma h is equal to Ka times gamma times h. So in this scenario here, I know Ka is 0.27, I know my gamma is 18, and I know my h is 3.5. So I can go through and I can just substitute these parameters into the equation, and I can calculate that my horizontal stress acting at the base of this retaining wall structure is 17 kPa. So if I want to calculate my total force that's acting per meter of the wall for the active case, I would use this formula here. Pa is equal to 1/2 times Ka times gamma times h squared. So I know Ka, I know gamma, and I know h. So I can go through and I can calculate my active force, which when I went through and did it, it worked out to be about 29.8 kilonewtons per meter. So my next step after calculating my active force would be to determine where this active force is acting on the retaining wall structure. So again, my horizontal stress distribution is triangular. So if I'm looking for the centroid of this triangle for a horizontal force, this horizontal force acts at a distance of h over 3 from the base of the retaining wall structure. So a distance of h over 3 from the base of the retaining wall structure is still 1.17 meters from the base of the retaining wall. So I would use the same process, and I haven't shown it here, but I would use the same process to go through and to calculate what my total horizontal force is in the passive case scenario. So if I was looking at my passive case scenario, my horizontal stress at the base of the sheet pile wall would be Kp times gamma times h. So if we know Kp is 3.7 times 18 times 3.5, 233.1 kilonewtons per meter, or sorry, is kPa, would be my horizontal stress that's acting at the base of the sheet pile wall for the passive case scenario. And then I would just use this formula here, PP is equal to 1/2 times Kp times gamma times h squared. And I could calculate what my passive force is for the passive case scenario. And it would act at the same distance from the base of the retaining wall structure at a distance of h over 3, because the horizontal stress distribution would be triangular as well. So I'm going to pause there and see if anyone has any questions on the calculations. Is this very similar to statics? Okay. Well, when you're starting to work through the example problems, if you have any questions, watch the videos, and then you can arrange a meeting with me if you want to discuss it further. So in most problems, sometimes you're given the Ka value or the Kp value. So your earth pressure coefficient, either in the active or the passive cases, but sometimes you're not. Sometimes you're only given your friction angle. But that's not a problem, because if you know your friction angle, you can calculate what your Ka or your Kp value is. So don't worry about all this writing on the left-hand side. This is what I want you to focus on. If you're given a friction angle in a problem and you need to determine what your active earth pressure coefficient is, to simply use that formula that I've highlighted in red, where Ka is equal to 1 minus the sine of your friction angle, which would be given in the problem, divided by 1 plus the sine of phi, which would be your friction angle as well. So your Ka value can be calculated using your friction angle. Same with Kp. Kp can be calculated using your friction angle as well. So Kp in this scenario here, again, don't worry about all of this on the left-hand side. I think it just makes it a little more confusing. Kp is just the reverse of your Ka. So Kp is equal to 1 plus sine phi divided by 1 minus sine phi, where phi represents the friction angle of your material, and that would be provided to you in the problem. You could also just calculate your Kp by using the formula Kp is equal to 1 divided by Ka. Kp is almost always greater than 0, and Ka is always, greater than 1, and Ka is always less than 1. So keep those two formulas in mind. You'll use them a lot. Okay, here's a brief discussion on when to use active or passive cases. So the active case is used for calculating the design pressure or force on a non-braced or non-anchored retaining wall structure. So if you don't see a brace, you don't see a tie-back anchor, then you always will use your active case scenario associated with your sheet pile wall. If you see a tie-back anchor or a brace, you're calculating your passive earth pressure. So your passive earth pressure in that scenario would be the calculation of the maximum force that can be applied by an external brace or tensioned anchor without failing the soil. Because imagine if you apply too much force to that soil mass, you're going to cause it to fail in an upwards and outwards direction. So you would have inward wall movement and an upward soil failure caused by those external forces. So you don't want to cause a soil failure or shearing of your soil behind your retaining wall structure. So you have to calculate the maximum force that can be applied by those tie-back anchors or those braces. So word to the wise, I'm not going to give you a passive case scenario on test number 4. I'm only going to give you an active case scenario. So I'm not going to be asking you to calculate anything associated with the passive cases. Sound fair?
So we don't have to worry about those formulas at all?
You have to worry about Ka is equal to 1 minus sine phi divided by 1 plus sine phi, because that's your active case scenario. Passive case, I'm not going to test you on, because it gets a little complicated with calculating the forces associated with those anchors or those braces. So don't worry about it. I just wanted you to be familiar and to be able to differentiate between when you would use your active case and your passive case scenarios. Seem fair? So concentrate on active.
Yep.
Okay. And that's why when Sean sort of asked the questions initially, when do you use active, when do you use passive? There are cases where you will have soil sort of on the left-hand side of your retaining wall structure. So if you do, and it's below 1 meter below the ground surface, you have to take your passive forces into account. Again, it sort of complicates the situation, and I don't think we need to go there. So again, don't worry, you'll never have to calculate your passive force on the left-hand side of your sheet pile wall, and you'll never have to calculate your passive force, in this course anyways, associated with a tieback anchor or an external brace. So we're just going to concentrate on your active case scenario. Okay. Anyone have any questions before we move on? Okay, so the horizontal stress profiles that we've talked about for the last 40 minutes or so, those have all been for cohesionless material. So say for a sand material or a sand or gravel material, and it's also been for scenarios where we don't have any groundwater pressure that's acting against our retaining wall structure. So this has simplified our problem and our process for determining what our horizontal stresses are at the base of the retaining wall structure and what our horizontal or what our total forces acting against the retaining wall structure are. I was going to go over a passive case scenario, but I'll ask you guys. It was example problem 12.3 where we had a tieback anchor, and I was going to go through the process just so you were familiar with it. That being said, you're not going to be tested on it. So do you want me to spend time doing that, or you can just go through that if that interests you? Let's go over it. Okay, this is example problem 12.3. We have tieback anchors along a retaining wall structure, and they're spaced 1 meter apart. So this problem is asking for what is the force acting on the wall if the anchors are pulling the wall into the soil, resulting in passive soil failure. And then it's asking for what is the angle of the potential failure surface. So in this scenario here, I've sort of drawn a very basic free body diagram showing that I have a 4 meter high retaining wall structure. I have 3 tieback anchors, and they're spaced at 1 meter intervals along the face of the wall. So you'll see in this scenario here, oh yeah, it's associated with problem 12.2. Our friction angle in this problem here is 34 degrees. That's the friction angle from our soil came from example problem 12.2. And the unit weight of our material is 15.6. So gamma bulk, 15.6 kilonewtons per meter cubed. And these parameters just came from example problem 12.2. So again, your KP value isn't provided, so we'll have to calculate our KP value. And our KP value is calculated or can be calculated if we know what our friction angle is. So in this scenario, KP is equal to 1 plus sine phi divided by 1 minus sine phi. So if we know that our friction angle is 34 degrees, we can just plug and chug through the formula, and we can calculate our passive earth pressure coefficient to be 3.54. So let's go down. So I've drawn my horizontal stress profile or my horizontal stress distribution for this retaining wall structure. My retaining wall is 4 meters in height, and I'll have a horizontal stress that's acting, and I've shown it here, acting at the base of this retaining wall structure. So I want to calculate this horizontal stress using my passive earth pressure coefficient. So I've calculated my passive earth pressure coefficient to be 3.54. My unit weight of my material is 15.6, and the height of my retaining wall structure is 4 meters. So I can multiply those parameters together, or those values together, and my horizontal stress at the base of the sheet pile wall is 220.9 kPa. So if I want to calculate what is the total horizontal force acting on this retaining wall structure in the passive case scenario, KP, yes. it would be PP is equal to 1/2 times gamma times KP times H squared. So that's my formula that I use to calculate my passive force. So I know that my unit weight's 15.6. I know the height of my sheet pile, or the height of my retaining wall, is 4 meters, and I know the unit weight of my material is 15.6. So the total horizontal force that's acting on this retaining wall structure for the passive case is 441.8 kilonewtons per meter. Again, my stress distribution is triangular in shape, so the centroid of that triangular shape would be at a distance of h/3 from the base of the retaining wall. So that horizontal force acts at a distance of 1.3 meters from the base of the retaining wall structure. Okay, I'm going to pause there to see if anyone has any questions. Oh, okay. Did you guys want a break, or do you want me to go over a scenario where we will have a material that has cohesion and the different process that you would use to calculate your active force and your horizontal stress? Break time, or? Oh, let's keep going. Okay. Okay. Okay, so let's think of the influence that soil cohesion may have on your horizontal earth pressure. So if soil has cohesion, this cohesion is actually beneficial because the cohesion provides additional strength that will inhibit a sliding failure from occurring. So this cohesion provides additional strength to your soil mass. So this additional strength actually reduces the active stress that's actually acting against the retaining wall structure. So there's two different scenarios. Obviously, we have the active case and the passive case. So in the active case, our horizontal stress at the base of the retaining wall structure is reduced everywhere by the value of 2 times C, where C represents the cohesion of your soil material, times the square root of your active earth pressure coefficient. Meanwhile, if we looked at the passive case scenario, your passive horizontal stress is actually increased everywhere by the value of 2C, where C represents your cohesion still, times the square root of your passive earth pressure coefficient. So let's take a look at this slide here. We'll take a look at your active case scenario. So you'll see for your active case scenario, if we look at even at the ground surface where we actually have 0 horizontal stress, our horizontal stress at that point is still reduced by the value of 2C times the square root of Ka. And our stress distribution profile is still linear, but our horizontal stress is actually 0 until we reach this point of inflection right here. And that point of inflection is a distance Z0. And we can calculate that distance Z0 by using this formula right here, where Z0 is equal to 2 times your cohesion divided by your unit weight of your soil material times the square root of Ka. So that point of inflection is an important point, and our horizontal stress distribution is decreased everywhere by that value of 2C times the square root of Ka. Whereas if you look at your passive case scenario, in your passive case, your horizontal stress is increased everywhere by your value of 2 times your cohesion times your square root of Kp. So if it's increased everywhere by this value, you still have your horizontal stress distribution profile, but in this scenario here, this 2C times Ka forms this rectangular shape. So to calculate your horizontal stress at the base of your retaining wall structure, it would simply be gamma times H times your passive earth pressure coefficient plus 2 times your cohesion times your square root of Kp. Whereas if you look at your horizontal stress at the base of your retaining wall structure in your active case, you calculate it by gamma times H times Ka, which is how we would normally calculate it, but then it's minus this 2C times the square root of Ka, because your active case is your horizontal stress is decreased by that amount everywhere. The process for calculating the centroid of your triangular distribution is the same. It would act, in the active case, it would act at 1/3 times H minus Z naught. So you have to take this distance Z naught into account. That's because your horizontal stress above this inflection point here is equal to 0. So you're only concerned with this triangular shape right here. So your active force acts at that distance of 1/3 times H minus Z naught. And your active force is 1/2 times gamma times Ka times H minus Z naught squared. So this is sort of the nuances or the differences when you have a material with cohesion adjacent to your retaining wall structure and a material that is cohesionless adjacent to your retaining wall structure. Are you guys okay if I go through an example problem using a material that has cohesion, or do you feel that you need your break? Okay, right. Oh, hold on. Okay, let's take a break. And then we'll come back and we'll work through this example problem. So let's take a break till 10:02. And then we can come back and work through this example problem, example problem 12.4, and then we'll sort of proceed with the remainder of the lecture. So come back at 10:04. How's the pace of today? Is it too slow, too fast?
I like the pace.
Okay, it's okay. Okay, let's get going. Switch back to the IPvo. Oh, yeah. Okay, example problem 12.4. It says the soil has a cohesion of 12 kPa and an internal friction angle of 15 degrees and a unit weight of 18 kilonewtons per meter cubed. What is the total active force on a 3-meter high wall? And it asks to draw the horizontal stress profile, and it asks what is the angle of the potential failure surface. So you'll see with this horizontal stress distribution, it's a little bit different than the ones that we've drawn in the past. You'll see initially we have our ground surface, but our horizontal stress is decreased everywhere by this value of 2C times Ka. So we sort of go into the negatives a bit, and our horizontal stress decreases from 0 to minus 2C times Ka. And our horizontal stress does increase linearly with depth until we reach our total height of 3 meters. But as I mentioned, there's sort of this point of inflection right here where we can calculate what that Z naught distance is. So that distance represents the portion of our stress distribution where our horizontal stress is actually equal to or less than 0. So we calculate this Z naught distance by using this formula, 2C divided by, where C represents your cohesion, divided by your unit weight of your material times the square root of Ka. Cohesion was given in the problem as 12 kPa. The unit weight of a material was given as 18 kilonewtons per meter cubed. And we can calculate our coefficient of earth pressure, our active earth pressure coefficient, because we knew our friction angle. So we can calculate our Ka value to be 0.589. So if we input all of these parameters into the equation, we can determine that that distance Z0, where horizontal stress is less than or equal to 0, is 1.73 meters. Anyone have any questions? How we determined our Ka value or how we determined what our Z0 distance is? Okay, to calculate what our horizontal stress is at the base of this retaining wall structure, we use this formula here where our total horizontal stress is equal to our active earth pressure coefficient times our bulk unit weight times the height of our retaining wall structure minus 2 times our cohesion times our square root of Ka. We know Ka is 0.589. We know our bulk unit weight is 18 kilonewtons per meter cubed, and we know the height of our retaining wall structure is 3 meters. We know that our cohesion is 12, and again, we know our Ka is 0.589. So we can go through and solve for our horizontal stress at the base of the sheet pile wall, and that's equal to 13.4 kPa. So that's our total horizontal stress at the base of the sheet pile wall, or sorry, at the base of our retaining wall. So our next step would be to calculate what is our total active force on this 3 meter high wall. So our active force, PA, is equal to 1/2 times our bulk unit weight times Ka times H minus Z0 squared. So it's important to recognize that you need to subtract your Z0 value from your total height of your retaining wall structure when calculating your active force that's acting on the retaining wall. So you can, again, the unit weight's 18, your coefficient of active earth pressure is 0.589. H is 3, so the total height of your wall is 3 meters, and your distance Z0 is 1.73. So your total active force acting on the sheet, or on the retaining wall structure, I keep calling them sheet pile walls, on your retaining wall structure is 8.45 kilonewtons per meter. And then I guess our last step would be to calculate or determine the distance at which that active force is acting from the base of your retaining wall structure. So again, we need to determine what is the centroid of this triangular shape. And we're just looking at determining the centroid of this triangular shape that is below your point of inflection there. So it would be H minus Z0 divided by 3. H is 3, Z0 is 1.73. So you can determine that your active force is acting at a distance of 0.42 meters from the base of your retaining wall structure. What is your angle of your potential failure surface? Again, this is sort of a review of what we did, what module would that have been, 6-ish or so, where theta is your failure surface, and that's equal to 45 degrees plus phi over 2. Phi is 15 from the problem, so your angle of your potential failure surface would be about 52.5 degrees. We don't have to focus on that so much. I'm not going to test you on that. That's just sort of a recall of previous material covered in the course.
Elena?
Yes.
When we write the test and we have to hand in work, are you going to require us to draw this out?
Yes.
Okay.
Yes. So I will ask you for free body diagrams, or I will ask you to draw your horizontal stress profile or your horizontal stress distribution, but I'll probably call it a horizontal stress profile. You will be required to draw all of it out. So all of the questions associated with the calculations associated with this test, you'll have to submit your work for, because you'll be drawing these stress profiles, you'll be calculating horizontal stresses, total forces or active forces, that sort of thing. So I need to be able to see what you're doing.
Okay, so for the majority of the calculation questions, we're going to have to hand in our work?
You'll hand them in for all of them.
All of them? Okay.
All of them. No, representative is good enough. I'm not a great artist, so as long as it's representative of the scenario, I'm okay with that. It definitely does not have to be to scale.
Is it gonna be a 1 hour exam or no?
It'll be slightly over 1 hour. It'll be either 1 hour and 15 minutes or 1 hour and a half. I haven't decided yet.
1 hour and a half sounds better, I think.
Yeah. Do you guys want it in the morning next week?
Yeah, morning's good.
Like at
Sounds
10
fine with
o'clock?
me.
Pardon me? Someone said Tim?
Yeah, at 10 o'clock, I like that.
Okay, we'll write it at 10 o'clock. Then you've graduated by 11:30.
We don't graduate until we get our diploma in the mail.
Well, I'll consider you graduated. Most of you already passed the course, so it's okay. Okay. Any questions on calculating your active force or your horizontal stress at the base of your retaining wall when you have soil with cohesion? No. Okay. When you're going through them, if you have any questions, just contact me. Okay. The next topic we're going to cover is unsupported vertical soil surfaces. I feel we don't spend enough time on this. I might look at expanding it in the future. If you can't remember anything that I taught you in this course for retaining walls, and this is the only thing you remember, I'm okay with that after you write test number 4. So please, please, please never enter an unsupported excavation that is, code is 5 feet or 1.5 meters, but even that, especially if you're smaller in statute, is pretty deep. So it's extremely dangerous to work in an unsupported trench. I'm sure you guys, every couple of years we hear a really sad story where someone, suffocated or was buried alive in an unsupported excavation and they didn't make it out. So it is really dangerous to work in an unsupported trench. You may think your soil seems stable, but maybe over time, maybe it rains, there's vibrations from heavy equipment, or there's weight from stockpiled material or weight from nearby equipment. It can cause that trench to collapse, and this material can fall on you. So every cubic meter of soil weighs 4,000 pounds. So death will be quick and by suffocation. Even if your head is exposed, likely your internal organs are going to be crushed and you're going to die. So I don't have Canadian stats, but in the US, 40 to 70 workers die each year due to trench collapse. And we usually hear of one in Manitoba a year. That's one too many. It really doesn't need to happen. So as the owner on a site, or if you're an on-site representative, you are responsible for worker safety. So never allow any workers that you're responsible for, or any workers on a site, even if you're not responsible for them, do not allow them to go in an unsupported excavation or an unsupported trench. So a trapped person. So as I mentioned, even if your head's sticking out, if you're trapped, your lungs can't expand, so you'll suffocate. And all your internal organs will be crushed, and you're likely not going to survive. There is guidelines for working and designing excavations. It's under the Manitoba Workplace and Safety and Health Division for excavation requirements. I can post the link, or I can put the link on Learn if you guys like. All shoring or all temporary excavation needs to be designed, sealed, and inspected by a professional engineer. So if your boss says, nah, it's all good, again, you have the right to refuse to enter that excavation or trench. So again, after test 4, if you don't remember anything else that I taught you for retaining wall structures, just remember this. And if you can remember this, then I was successful. Any questions?
What was the height you said?
It's 5 feet is what the provincial guidelines are. I think that's a little high because some people are barely over 5 feet, right?
Yeah, you'd think it would be like half your height.
I would think 3 feet is
Yeah.
what it would be, because then most people that would come up to their waist, right? And you wouldn't be crushing internal organs in your lungs and that sort of thing. Again, you do have the right to refuse to enter any excavation or any trench if you feel it's unsafe. And there's guidelines depending on the different material types as well. But
I actually just had one of my old bosses about 2 years ago. He just died this exact same way.
was that the one in Springfield?
Yeah, there was just
Yeah.
two. They were both owners of different companies, and they dealt with concrete and excavations, and they had done it for 30, 40 years, and they were very well knowledged in everything, and they just dug out the hole. It was too small for shoring, and he hopped in, and it collapsed, and it took him minutes, and he was dead.
Yeah. So there you guys go. It can happen to anybody. It can happen to the most experienced, and you may think you're safe and you're not. So never, ever, ever, even if someone tells you it's safe, don't ever do it. You have the right to refuse. So as I mentioned, if this is all you take away from the course, oh goodness. Yeah, that's really sad. I hope none of you ever have to experience this. Okay, well, let's move on to something maybe a little more uplifting. So there are scenarios where you may have a high water table that is acting on your retaining wall structure. So to date, we've only discussed retaining wall structures and the backfill material that would be considered well drained, or backfill material that doesn't have any excess pore water pressures associated with it. But what do you do when you actually have backfill material that's saturated and you're going to have a pore water pressure associated with it? You recall back to module 4, we calculated what effective stresses were. And remember, I said when we're calculating our total horizontal stress, we always use our effective stress. So in the case of well-drained soil, we've never been taking pore water pressure into account. That's because our effective horizontal stress is equal to our total horizontal stress because there was no pore water pressure associated with it. However, when you have a high groundwater table, your total horizontal stress, and we covered this in module 4, is equal to your earth pressure coefficient, so either active, passive, or at rest, times your buoyant unit weight, times the height of your retaining wall structure, plus you have a water pressure term. So your total stress would include plus gamma W times H, where gamma W represents the unit weight of water. And we went over this in module 4. So how do you incorporate this water pressure term into your calculation for your total force per meter? Same way, your water pressure would be triangular in distribution as well. So you would have a formula that you would just expand, and you would calculate your total force using this formula here, where you still have your Ka, but your unit weight now is a buoyant unit weight instead of a bulk unit weight. The height of your retaining wall structure is still the same, but you have to add this water pressure term. So you use the unit weight of water and you use the height of your retaining wall structure. And the height of your retaining wall structure is squared. And then you have 1/2 because we're talking about a triangular distribution. Okay, let's go over example problem 12.7. And I'm going to ask you some questions about it. Okay, so 12.7 is comparing horizontal forces for a high water table and well drain cases. So the retaining wall structures are exactly the same in height. They're 3.5 meters in height. So we're going to compare the total force due to active earth pressure for the well-drained soil. So it would be a sand material. The material properties are given there. You have a friction angle, you have a bulk unit weight, and it gave you, or sorry, a dry unit weight, and it gave you gamma sat, or sorry, your saturated moisture content. Compared to one that has a water table at the ground surface. So let's talk about the well-drained scenario. So when you have a well-drained scenario, it means your water table is below the base of the wall. So if your wall is 3.5 meters in height, your water table is below that. So it doesn't come into play when you're designing your retaining wall structure. The first step would be to calculate your active earth pressure coefficient. We can use our handy dandy formula. The only parameter we need to know is our friction angle, and our friction angle was given in the problem as 38 degrees. So we can calculate our Ka value, and that works out to be about 0.238. The next step would be to calculate for the well-drained scenario, to calculate our horizontal stress at the base of the retaining wall. We have our triangular distribution. We're going to calculate our horizontal stress, which is at the base here, and that's simply equal to our active earth pressure coefficient times gamma bulk, because it's a well-drained soil, times the height of our retaining wall structure. So our Ka value, we calculated it to be 0.238. Our unit weight is 17.4 kilonewtons per meter cubed, or sorry, it's 17 kilonewtons per meter cubed times 3.5 meters. And I just calculated what your unit weight would be for the material. Probably, sorry, it should be probably 17.2, but I'll go through it. And so yeah, assume it's 17.2. I made a mistake there, sorry. Times 3.5. So your horizontal stress at the base of the retaining wall structure is 14.3 kPa. So we also need to calculate what our total horizontal force is acting on the wall. So our total active force, we use this formula here, our standard formula. We know Ka, we know our unit weight of our material is 17.2, and we know the height of our sheet pile wall, or of our retaining wall, is 3.5. So we know our total active force that's acting on the retaining wall structure is 25.1. Yeah, we're just assuming here, Fabian, there wasn't enough information given to calculate what it would be. They didn't give you a moisture content, assuming that it wasn't saturated. So I just used the value that was given. Don't get hung up on that. I'm not going to ask you guys to go through the process on a test to calculate what unit weights are, because that's not what I'm really testing on this material. So yeah, don't get hung up on that. So yeah, we have a 25.1 kilonewtons per meter, and it's acting at 1.17 meters from the base of the wall. We know it's a triangular shaped distribution, and we know our centroid's at 1/3 times h/3. Nope, Pavel, you can't calculate it. There's not enough information. So we know it's at 1.17 meters from the base of the wall. So this is for the well-drained scenario. It's exactly the same scenario that we've worked on in the last hour. Yeah, so you're not in the saturated in the well-drained scenario because we don't have any pore water pressure associated with it. Inherently, there would be some water content associated with the soil, but it wasn't given, and only a saturated moisture content was given. So don't get hung up on those details. So let's look at a saturated slope. So if we consider a saturated slope, we consider that our groundwater table is at the top of the retaining wall structure. So if our retaining wall structure is 3.5 meters in height, our groundwater table is at the top of that retaining wall structure. So now we have two horizontal stresses and two forces to calculate. We have the horizontal stress and force associated with the soil. Okay. And we have our horizontal stress and force associated with our water pressure. So for this example problem here, I went through and I calculated what our gamma sat would be, and it's 20.5 kilonewtons per meter cubed. I simply just multiplied gamma bulk times 1 plus our moisture content. Our Ka value remains unchanged. And the reason why Ka remains unchanged is because we still have the same friction angle. So we still have a friction angle of 38 degrees. So our Ka value is unchanged. So I have to draw two stress distributions here. I have a stress distribution associated with the soil, and I have a horizontal stress distribution associated with our pore water pressure. So if we take a look at the soil, stress distribution, again, is triangular in shape. I can calculate my total horizontal stress at the base of the retaining wall due to the soil. I simply calculate it the same way as always, is equal to Ka times gamma buoyant times H. I know what Ka is because I solved it for above. I know gamma buoyant, I would calculate it by using gamma sat minus 9.81. And I know the height of my sheet pile, or the height of my retaining wall is 3.5. So my total horizontal stress is 8.9 kPa due to the soil. Again, I would take a look at the horizontal stress profile associated with the water. My total horizontal stress is equal to gamma W times H. Gamma W we know to be 9.81 and H is 3.5. So I know my total horizontal stress at the base of the retaining wall due to the water is 34.3 kPa. So I know my total horizontal stress is therefore my horizontal stress associated with the soil and my horizontal stress associated with the water. So I'm just adding those two values together, and my total horizontal stress at the base of the wall is 43.2 kPa. So I'm now going to look at how do you calculate the horizontal force associated with both the soil and the water. So my total force is my total active force associated with the soil, in addition to my total active force associated with the water. So I know that I calculate my total active force associated with the soil by using this component of the equation, where it's 1/2 times Ka, which I know Ka. I know my gamma buoyant, and I know H, plus 1/2 gamma W, which is the unit weight of water, times the height of my retaining wall. So I solve for it back down here. I know Ka. I solve for it above is 0.238. I can calculate gamma buoyant, so it's my saturated unit weight minus my unit weight of water times the height of my retaining wall structure squared, plus 1/2 times the unit weight of water, which is 9.81, times the height of my retaining wall squared again. So I calculated my total active force acting on this wall to be 75.7 kilonewtons per meter. And I know my horizontal force acts at a distance of 1/3 H from the base of this retaining wall. Both of the stress distributions are triangular, and the base, so the distance from the base is simply H over 3, which is 3.5 divided by 3. So it acts at a distance of 1.17 meters. Here is 1.17 meters, and here is 1.17 meters from the base of the retaining wall.
What does it say under your PA total there? Papers.
Oh, from base of wall.
Okay.
So acting at 1.17 meters from base of wall. So what do you guys notice about your well-drained, what do you notice about the differences in your horizontal stresses and your active forces associated with the well-drained scenario versus your saturated slope?
Saturated are a lot higher numbers.
Exactly. So do you think this would be cause for concern if you have greater forces acting on your wall trying to push it like outwards and downwards? You think that's a positive to have water against the retaining wall structure, or a negative?
Definitely a negative.
Yeah, so you have more force acting against the wall, trying to overturn the wall, trying to cause it to slide. You have greater stresses at the base. It's just all a recipe for causing potential instabilities.
So would it be a valuable thing to add significant draining around the area?
Yes, exactly. So you would add, you could add some sort of drain structure with a drainage pipe. You could use different types of backfill. So you could use more granular type backfill. You would put something similar to a chimney drain. You would have a longitudinal drain in there. You would put like impervious material on top if you have some common backfill in there to reduce the amount of infiltration into the backfill material that's adjacent to the retaining wall structure. Yes, water for a geotechnical engineer is our enemy. It causes a lot of issues. Anyone have any questions on this example problem here? So drawing these horizontal stress distribution profiles, they seem quite similar to drawing a vertical stress profile, right? From module 4, very similar. So let's take a look at this. So this is what it's saying is your horizontal stress at this point right here at a distance of 3.5 meters below the base of this retaining wall structure is 34.3 kPa. So it's going to be the same. Remember how we did this, where we had versus depth, and we used to draw it like this, right? And we'd have a value. So instead of it being sigma V prime, it's now sigma H, right? So we have a depth of 3.5 meters, and then we would have a total horizontal force at that point. See the correlation?
And so why not just draw them both in one and just have one for the total?
You can. Yeah, I just broke them out so that you could see the difference, but you're more than welcome to draw it as one. So if you're more comfortable drawing it as one, I'm okay with that. Okay, well, let's move on. There's one other scenario that we could potentially see when we're designing retaining walls, and that would be a horizontal stress due to a surface load Q. So imagine if you were designing a retaining wall structure, but you were going to place some embankment fill above it, or you were going to have heavy equipment that was running on top of the retaining wall structure, or you were going to put houses, or or anything that would load the top, or any sort of surface load at the top of the retaining wall structure. You need to design for that as well. So that additional horizontal stress due to the surface load is constant with depth. So instead of being sort of being triangular in shape, like our horizontal stress distribution, it is more rectangular in shape. So that value of Q isn't changing with depth. It's constant. So it forms this sort of rectangular shape right here. So this represents your Q value. And you calculate what your horizontal stress would be associated with that surface load Q by multiplying it by Ka, so your active earth pressure coefficient, or Kp if you were designing in the passive case. So your horizontal stress due to the surface load can simply be added to the stress due to the soil's self-weight. So the triangular portion would represent the soil's self-weight, and this rectangular portion would represent the surface load. Surface load is always reported in kPa or in kilonewtons per meter squared because it's a stress. Similarly, or I guess a little bit differently than your horizontal stress profile associated with the soil's self-weight or overburden pressure, your centroid for this rectangular shape is a little bit different. The centroid location is at a distance of h/2 from the base of the sheet pile wall. And that's the same in both your active and your passive case. So if we look at it here, this portion represents the soil self-weight or the overburden pressure. Your total force acts at a distance of h/3. So this total force here acts at a distance of h/3. And this force here represents at a distance of h/2. So the location of where those forces act is slightly different. You can, if you want, determine an overall location, or but I'm not going to ask you guys to do that. But I'm assuming you guys did that in statics, looking at different shapes and sort of taking an average of them to determine where your centroid would be located for sort of more of that trapezoidal shape. Did you guys do that? No? Okay,
Yes,
well-
we have, but it's been a while.
Yeah, it's been a while. Let's just focus on being able to determine the location of your centroid for a rectangular shape or square shape versus a triangle shape. Yeah, first year. The structurals were all over it. When I taught foundation design last term, they were all over. We were integrating and doing whatever. It hurt my brain, actually. They really like math. Okay, let's work through example problem 12.9. This is the full meal deal. This is the most complicated problem that you'll ever see in this course. So I think this is a really good problem to be working through. So example problem 12.9 is asking you to find your active pressure resistance. So your active force for a 4-meter high wall. You have a water table at the top of the wall. The soil is a silty sand, so you have a friction angle of 30 degrees and a buoyant unit weight of 12.8 kilonewtons per meter cubed. The top of the sand is loaded by a structure that exerts an average surcharge load or an average pressure Q of 120 kPa on the ground surface. So we need to determine what our total horizontal stress is at the base of the retaining wall structure and what our total horizontal force is that's acting on this retaining wall structure. So where do you guys think we should start? How many different shapes are we going to have? So what do we need to consider? We'll have a shape associated with what?
The uniform load.
Right, the uniform load, so your Q. What about water? Are we going to have a shape, like a stress profile associated with the water?
Yeah, with the water and one with the soil.
Correct. So you'll have 3 different stress profiles. You can combine all of them together if that makes you more comfortable. I'm happy to review your work like that as well. So I've shown 3 different shapes here. You have your rectangular shape from your surcharge load, and you also have a triangular shape from your soil and water. So I've combined mine here as well. And if it doesn't make you comfortable to combine, I've drawn a third one over here, and this will represent your water stress profile, horizontal stress profile. So to calculate our horizontal stress at the base of this retaining wall structure, we have Ka times Q, so this represents our surcharge pressure or surcharge load, times Ka times gamma buoyant times H. So this represents our soil that is saturated, plus gamma W times H. So this represents the horizontal stress associated with the pore water pressure. So we can go through, we know Ka because we know that our friction angle was 30 degrees, so we could solve for Ka. When you're doing your calculations for Ka, if you have a really high Ka value, double check your calculations. You should be around the 0.3-ish range. If you don't have something around the 0.3-ish, double check those numbers. We know Q is 120. That was given in the problem. So again, plus Ka, we know Ka. We know gamma buoyant, that was given in the problem. We know the height of the wall, that was given in the problem. And then that's plus, and the unit weight of water, so we know that is 9.81 times the height of the wall. And so that's 4 meters. So we can add the horizontal stress associated with the surcharge load, this overburden pressure, and then plus our pore water pressure. And our total horizontal stress acting at the base of the wall is 96.2 kPa. Okay, any questions on how or why we did these calculations associated with the horizontal stress at the base of the retaining wall? No, okay. Next step, we need to calculate what is our total active force associated with the scenario. So we'll have an active force associated with the soil, we'll have an active force associated with the water, and we'll have an active force that's associated with our surcharge load. So I did the soil and water to come together. So my active force associated with the soil and water, I use this formula right here, 1/2 times the active earth pressure coefficient times the buoyant unit weight times the height of the retaining structure squared, plus 1/2 times the unit weight of water times the height of the retaining structure squared. I know my Ka is 0.33, and I calculated that above. I know my buoyant unit weight, it was given, it's 12.8, and I know the height of my retaining wall structure is 4 meters. Plus 1/2 times the unit weight of water, which is 9.81, times the height of my retaining wall structure, which is 4 meters. So my total active force associated with the soil and water, which has the triangular shape distribution, is 112.5 kilonewtons per meter. And this acts at a distance of h/3 from the base of the retaining wall. And we know that retaining wall is 4 meters in height, so h/3 is equal to 1.33 meters. Any questions on calculating the active force associated with the soil and water for this scenario?
Makes sense to me.
Makes sense. Okay. Okay, so now let's calculate the active force associated with the surcharge load. So the active force associated with the surcharge load is simply equal to Ka times Q times H. We know Ka, we calculated that, that's 0.33. We know Q, it's 120, it was given in the problem, and we know the height of the wall is 4 meters. So therefore, our total force associated with our active force associated with the surcharge load or surcharge pressure is 159.8 kilonewtons, and this acts at a distance of h/2. So the height of our wall is 4 meters. We're looking at a rectangular shape, so that centroid is about half of that height. So it's at 2 meters from the base of the wall. So to calculate my total active force associated with the scenario, I have to add the soil and water plus the surcharge force. So the soil and water is 112.5, and the surcharge force, so a force associated with the surcharge load is 159.8. So my total active force for this scenario is 272.3 kilonewtons per meter. And for those who are interested, you can determine the location of your centroid. This is just for those who would be interested. Times 2, sorry, that's not going to show up. I started earlier. Bringing back first year. could use that formula there if you wanted to determine sort of the location of your centroid associated with the triangular base distribution and the rectangular base distribution. Sorry, that's not 2.72, it's 272.3. For those who are interested in bringing back, I don't know if you had pleasant thoughts from statics and strength of materials, or if it's just bringing back some nightmares. I'm not going to ask you to do calculations to determine where your overall active force would act against the wall, but for those who are interested. Any questions? Okay, you know where to find me. One more slide. Sloping ground and friction between the soil and the retaining wall, Rankine versus Coulomb. So we've been using Rankine and the theory behind Rankine for doing our calculations associated with the retaining wall structure. There are factors that may influence the horizontal stress acting on a retaining wall, and this could be, you could have a sloping ground surface. So you could have a sloping ground surface. So this right here, you could have friction. You could have some friction acting between the retaining wall and the soil, or you can have a sloping interface between the wall and the soil. So you could have a sloping interface here. So all of these may influence the horizontal stress acting on the retaining wall structure. Using Rankine, we've neglected the sloping interface between the wall and the soil and the friction between the retaining wall and the soil. There is a chart you can use to determine how your sloping soil surface may impact your Ka value. That we're going to remove from the course this year. I just wanted you to recognize that we've been using the Rankine method. If you were to use the Coulomb method, you would take all of these factors into account, and the design process would be a little bit different. But just recognize there are some limitations to the methodology that we've used. And there are other methods that some people may use to calculate their forces associated with a retaining wall structure. So that's what I have for this material. Example problems 1210, 1211, 1212, you won't be responsible for doing, nor will I test you on the material.
Sorry, can you tell Elena which one?
1210, 1211, and 1212. You won't be responsible for doing those example problems.
What about 12.6?
12.6. 12.6 is the same as 12.7, except it has your groundwater table at the ground surface. So yes, it would be the same as 12.7, where we looked at the saturated slope.
Okay.
So yeah, that would be fair game. I did 12.7 because I wanted you guys to appreciate the difference between a well-drained slope and one that's saturated, and how that may impact the stability of your retaining wall structure. Okay, I think you guys probably need a little bit of a break. We have still some theory to go through. It never ends in this course. So do you guys want a 10-minute break and come back at 11?
Sure.
Or you want to keep powering?
Nope.
Nope. Okay. So
So
guaranteed,
we have about 1 hour?
you'll have about another hour after this. Yeah.
Okay, sounds good.
So guaranteed, you will have some questions associated with calculating, like drawing your horizontal stress profile and calculating your horizontal stresses and forces associated with scenario. So likely you'll have a saturated slope, likely you'll have a surcharge load, and you will have to draw a horizontal stress profile. Have an appreciation or an understanding of how the surcharge load and pore water pressure have an impact on your retaining wall. This is the fundamentals of retaining wall design in 2 hours. I know it's a lot. I'm sorry, guys. And so 10-minute break, and then we'll come back, and then we're going to look at calculating your factor of safety for cantilever and gravity retaining wall structures for sliding and overturning, and to confirm if your design is successful. So take a 10-minute break, and we'll come back at 11. I don't get it. Everyone in my neighborhood is retired, so I don't know why my internet went down. We'll give everyone a few minutes. Obviously, my internet and my computer are done for the day, obviously. Okay, I think we've lost a few, but I'll just give a bit of a brief overview on designing drainage for retaining walls. So as I think Sean asked previously, can you put some free draining backfill material or a longitudinal drain against your retaining wall structure to reduce the pore water pressure? Most definitely. So if you're using common backfill as backfill material adjacent to your retaining wall structure, I recommend you use granular fill material, usually with a geosynthetic and also a longitudinal drain. That will help reduce the pore water pressures against your retaining wall structure. It's also a good idea to have an impervious layer immediately above the sheet pile or above the retaining wall structure. That impervious layer inhibits or prevents as much subsurface infiltration into the material that's adjacent to the retaining wall structure. You can also use free draining backfill material, so a free draining sand or gravel material immediately adjacent to your retaining wall structure to reduce pore water pressures as well. So that's a way you can reduce pore water pressure to minimize the potential for any instability issues, such as overturning or sliding with your retaining wall structure. These are some just basic types of retaining wall structures. So you'll see examples of these in the first PowerPoint presentation, along with photographs showing what they look like. For this portion of the course where we're calculating factor of safety, we're going to focus on gravity and we're going to focus on cantilever retaining wall structures. But in the first PowerPoint, you'll see examples of mechanically stabilized earth retaining wall structures. You'll also see examples of sheet pile walls. You'll see examples of soldier pile walls, modular walls, and various other types of retaining wall structures. How many people do we have? 22. Okay. So now we're going to focus on the design of gravity and cantilever retaining wall structures. So gravity and cantilever retaining walls must be designed for the resistance to both sliding and overturning. So you can differentiate between gravity and retaining wall structures in the sense, or sorry, gravity and cantilever retaining wall structures in the sense that a gravity retaining structure doesn't have a component of soil that acts on the base of the sheet pot or the base of the retaining wall structure. So you'll see with this cantilever structure here, there's a soil mass that acts on a portion of the retaining wall structure. So that mass of soil is preventing that retaining wall structure from overturning and sliding. So it's providing some resistance. So if you think of factor of safety in terms of resisting forces divided by driving forces, that soil mass is providing a resisting force and providing shear resistance to both overturning and also sliding. Whereas a gravity retaining wall structure, it doesn't have that soil mass that's acting on the actual concrete portion of the retaining wall structure. So that's how you can differentiate between a gravity and a cantilever retaining wall. Okay, gravity wall design, we look, and same with cantilever wall design, we look at two components. The first one is resistance to sliding. So again, think of factor of safety in terms of what are your resisting forces versus what are your driving forces. So we always want our resisting forces to be greater than our driving forces, and ideally we want them to be 1.5 times greater than our driving forces. So that's our traditional definition of factor of safety. If our shear strength or our shear resistance is significantly higher than what our driving forces are, then we would consider our retaining wall structure to have an acceptable factor of safety. So if we look at the shear resistance of our retaining wall structure here, our shear resistance can be found along the base of our retaining wall structure. So shear resistance is equal to the weight of your retaining wall structure. So the weight is, I'll show you how you go through and do those calculations, but it's related to the shape of the structure and also the unit weight of concrete, plus any forces that are acting in the vertical direction. So if you have any other additional forces that are acting in the vertical direction, times your tan of psi. And psi represents your concrete soil friction angle. So your psi value would always be given to you in a problem. You would never be expected to determine what your psi value is. If you are curious, your psi value does vary depending on what your soil type is. So if you have a silt material, the friction angle between your silt material and concrete is lower than it is for, say, if you had concrete interacting with a coarse sand or a gravel. Your minimum embedment depth is usually 1 meter. So most retaining structures will have a minimum embedment depth of 1 meter. Sometimes they are designed to be greater. The embedment depth is designed to be greater than your frost depth, which in our case is usually 2.5 meters or so. Again, don't worry about that. We're not going to go through the calculations associated with determining what your embedment depth is. But what I just want you to know is, okay, factor of safety for sliding is your shear resistance divided by your driving forces. Your shear resistance is the weight of your gravity retaining structure multiplied by the tan of your friction angle, which is your concrete soil friction angle. And that's divided by your driving force. So your driving force is the force that's trying to cause your retaining structure to slide. So your driving force is this pH. And what would your pH be equal to? What did we calculate in the last 2 hours that our pH in this scenario would be equal to? What's our driving force for a retaining wall structure?
The mass of the soil and water.
Yeah, so it's our active force that is acting on our retaining wall structure, exactly. So if there's water, if there's soil, if there's a surcharge load, that is our active force that is acting on our retaining wall structure. So that is our driving force. So we want our resisting force divided by our driving force to be greater than 1.5. So if we look at our resistance to overturning, again, we can think of it in terms of factor of safety. So we always want our resisting forces to be greater than our driving forces. So in this instance, for the design of a gravity retaining wall structure, we're going to use the location of the reaction. So when we're looking at location of the reaction, it must be in the middle third of the base of the wall. So this value D, so the distance D from the toe of the retaining wall structure to this distance right here represents a distance D. And D is calculated by taking the sum of the moments about the toe of our retaining wall divided by the sum of our forces in the Y direction. So the sum of the forces about the toe would be the weight of your retaining wall structure plus any forces that are acting in the vertical direction minus any forces that are acting in the X direction. And you take their moment arms associated with each of those different forces divided by the weight of your retaining wall structure plus PV. So that's any forces that are acting in the vertical direction. We don't usually have anything other than the weight of our retaining wall structure. So we generally don't have any forces that are acting in the vertical direction. So usually PV becomes 0 and in our example problems. Yes, and I find this confusing. PX is exactly equal to PH. So, and that's one thing I wanted to point out. I tried to change this in the PowerPoint slide, but it wasn't letting me change it in the equation editor. But PX is equal to PH. So if I were you guys, I would cross out PX and write in PH in this formula right here. And PH, again, is equal to any force that's acting in the horizontal direction that's trying to cause this retaining wall structure to overturn. So that would be any of your active forces that are acting in the horizontal direction. So that would be any active forces associated with surcharge load, water, or the soil self-weight or overburden pressure. So that's how you would determine where your location of your reaction D is, and that's a distance from the toe of your retaining wall structure. So this would be a distance D. This is the toe of your retaining wall structure. You would calculate this distance D. And so 1/3 times B, where B represents this would represent B. The length of your retaining wall has to be less than or equal to D, which has to be less than or equal to 2/3, right, times B. And we'll go over a couple example problems associated with doing these calculations. So let's go over one example problem. We'll go over one with a gravity retaining wall structure, and we'll go over one with a cantilever retaining wall structure. Any general questions on the theory before I go over the example problems?
So B is the width of the base, not the distance from the toe to the vertical pressure force?
Correct. B is the distance along the base of your retaining wall structure. That is correct. So again, it would be good to have an understanding of these free body diagrams where the various weights associated with your retaining wall structure and where you're associated with your soil mass and water and surcharge load would act on your retaining wall structure. And I'll go over example problems and what your free body diagram should look like. Okay.
Would they ever anchor those to solid rock structures that are, say, nearby?
Yes.
Yeah.
So if they determine, so they would anchor them if they need be to provide that resistance to overturning or sliding. Yes, most definitely.
Is that just in, say, a case where the factor of safety is too low?
Yes, correct. And you need some additional force to ensure that your wall's stable. Exactly. So if you have a large soil mass that's acting against your retaining wall structure, you would anchor it. Yeah.
Okay.
Good question.
Is that kind of how the Hoover Dam works?
I don't know. I'd have to look that up. Is it anchored? I'm not 100% sure.
It's in between those two rock structures, right? So.
Yeah, I'll take a look and I'll get back to you. I don't 100% know, actually.
I think the sheer amount of concrete in the Hoover Dam would weigh it down enough to hold it in place.
I have a picture of myself. I actually I can envision it because I went there probably, I don't know, 12 years ago. And there's a picture of me during construction and it looks like I'm holding it up. I don't know if you guys did that picture. I don't know if that road's still there because this was 12, 13 years ago. Okay. So this is example problem 1215. It's a cantilever retaining wall structure, and it's asking you to calculate the factor of safety for sliding and the location of the resultant on the base, which is your resistance to overturning. So with each of these different example problems, it's recommended that you draw sort of a free body diagram. So you'll see here over on the right-hand side, I sort of redrew the structure. And so I identified what the length of the various components of the structure would be, and then where would my centroid associated with those various shapes act. So I have, I've divided my area into 3 different shapes. So you'll see here, I have one rectangular shape associated with the retaining wall structure. I have another rectangular shape along the base that's associated with the retaining wall structure. And then I have a third shape. Pull this side. And this third shape over here, this pencil just died. Not a good day. I have 3 pencils that just died. Okay, the third shape here is associated with the soil mass that's immediately adjacent to the retaining wall structure and sitting on the base of this retaining wall structure as well. So this is for a cantilever retaining wall only. So I have 3 shapes, shape 1, shape 2, and shape 3. So I've redrawn my structure. This represents shape 1, this represents shape 2, and this rectangle here represents shape 3. And each of these different shapes have different lengths and different widths. So I've drawn that out and I've shown where the weight would act for each of the different shapes. So the weight for each of the different shapes would sort of act in the center of the shapes. So, and those weights of those different shapes represent either soil or concrete, and they would provide a downward force. You also see here, I have a horizontal stress profile that represents the soil distribution as well to the right of that soil mass there. So my first step in my problem, I've also dimensioned my problem as well. So the first step in my problem would be to determine what my Ka value is. So in this problem here, I have granular backfill. I was provided with a friction angle of 35 degrees, so I could include that in my Ka formula to calculate what my Ka value is, and that's equal to 0.271. My next step here would be to calculate what is my horizontal force, or what is my Pa value associated with the soil, with the overburden stress of the soil material adjacent to the retaining wall structure. So pH, or Pa, is equal to 1/2 Ka times your bulk unit weight, because there's no pore water pressure associated with this scenario, times the height of your structure squared. So the height of our structure here is 6.1 meters. It's 5.3 meters from here to here, and then the height of the base of my retaining wall structure is 0.6 meters. So the height overall of my retaining wall is 6.1 meters. So I went through and I calculated that value, and my pH or my PA value is equal to 102.9 kilonewtons per meter. So I'm going to do my first calculation, which is my factor of safety against sliding. So I know my factor of safety against sliding. I use this formula here, where it's really what is my shear resistance or my resistance to sliding. And that is this resistance to sliding along the base of my retaining wall structure here. And that's equal to W plus PV times tan psi divided by pH. Well, in this example problem here, W is represented by 3 different shapes. I have a W associated with shape 1, a W associated with shape 2, and a W associated with shape 3. Well, you're probably wondering, how do I calculate what these W values are? These W values represent a load, so a force associated with each of the different components. And we provide it in units of kilonewtons per meter. So in this problem here, shape 1 is this rectangular portion of this gravity retaining wall structure. The unit weight of concrete we've used is 22.8. The height of that rectangle is 5.5 meters, and the length of that rectangle is 0.6. So I can go through and calculate the weight of this rectangular portion identified as 1, and it's 75.2 kilonewtons per meter. I then would calculate what is the weight of my second rectangle, just this rectangle here. So again, it would be the unit weight of concrete, which is 22.8, times 3.7 meters, times 0.6 meters in height. So the weight associated with my second rectangle is 50.6 kilonewtons per meter. The weight, I would have one more rectangle, and it's this rectangle in here associated with the soil mass that's acting on the base of the retaining wall structure. So the unit weight of my backfill is 20.4. The length of this area in here is 2.5. It's simply 3.7 minus 0.6 minus 0.6. So that's 2.5 meters times 5.5 meters in height. So the weight associated with area 3 is 280.5 kilonewtons. So I don't have any other forces that are acting in the vertical direction. So if I look at this equation here, my PV value goes to 0. I don't have any other forces associated in the vertical direction. And generally I don't with the problems that I'll give you. So you can go through and solve for your factor of safety. So you know W1 is 75.24, you know W2 is 50.6, and you know W3 is 280.5. You know your psi value is 26 degrees, so you take the tan of 26, and then you divide that by your pH value. And you know your pH value is equal to your PA value, and you calculated PA above, and that's 102.9. So you've calculated your factor of safety to be 1.93. And because your desired factor of safety is 1.5, and you've calculated a factor of safety of 1.93, you would say that your factor of safety against sliding is acceptable. So I'm going to pause there on the factor of safety against sliding calculation and ask if anyone has any questions.
Where did you calculate PA? Did you just not write it down?
PA is right here. So pH is equal to PA.
Oh,
Which
okay.
is, yeah.
What was the angle there?
The angle, the friction angle or psi, so the angle of friction between the concrete and the soil.
Okay, I see it there. Thanks.
Yeah, yeah. Everyone's okay with the factor of safety against sliding? So if you're drawing this out as a free body diagram, I think it'd also be good if you could identify that along the base of this retaining wall structure, you have shear resistance, so an R value that represents your resistance to sliding. So if you were drawing this out on a test and you didn't have room to draw that shear resistance along the base of your retaining wall structure, you can draw it below, say, your B2 illustration. Just indicate to me where you would expect to see some resistance to the sliding along the base. The next calculation you would need to do is your factor of safety against overturning. So your factor of safety against overturning is the sum of the moments about the toe of your retaining wall structure. So the toe of your retaining wall structure is really here. It's always, toe of your retaining wall structure is here. Bottom left-hand corner of your retaining wall structure. The sum of the moments about the toe divided by your forces in your Y direction. So if you're going to calculate the sum of the moments about the toe, you need to also calculate the distance of your lever arms. So if I'm looking at shape number 1 and the distance of those lever arms from the toe of your retaining wall structure. So I'm always comparing all of my forces to this bottom left-hand corner. So how far is it the sort of the centroid of this shape from the toe of this retaining wall structure? So if I look at shape number 1, so this represents shape number 1 here. Shape number 1, the centroid of shape number 1 would be in the middle of that shape. And it's kind of hard to tell from here, but the distance from here to here is 0.6 meters. And then the width of this rectangular shape number 1 is 0.6 meters. So the centroid of that is 0.6 meters plus 0.6, which is the width of triangle 1 divided by 2. So the distance x1 from the toe of the slope to the center of triangle number 1 is 0.9 meters. If I look at shape number 2, which represents this shape down here, the distance or the length or width of that shape is 3.7 meters. And the distance from the toe of the retaining wall structure to the center of this rectangular shape would simply be 3.7 meters divided by 2, which is equal to 1.85 meters. If I look at shape number 3, the center of shape number 3 would be right here. Again, it's a little confusing from the diagram here, but this distance here is 0.6. This distance here is 0.6. And then I know this distance in here is 2.5 meters. So to calculate the lever arm for W3 from the toe of the slope, it's simply B3, which is the width of this third rectangular shape, which is 2.5 divided by 2, plus 0.6 plus 0.6. So x3, so the distance from the toe of your retaining wall structure to the center of that third triangular shape is 2.45 meters. Okay. So now if I'm going to sum the moments about the toe of my retaining wall structure, it's simply W1 x1 plus W2 x2 plus W3 times x3 minus my active force times h over 3, because the distance from the toe of my retaining wall structure to where my PA force acts on my retaining wall is at a distance of h over 3 from the base of the retaining wall structure. So I've calculated that distance to be 2.03 meters. And that's simply divided by W1 plus W2 plus W3. And so I've calculated W1, W2, and W3, and I've determined what X1, X2, and X3 are, and I've calculated what PA is above. So I go through and I plug and chug through my numbers, which I've shown here. So W1 was 75.2, X1 was 0.9, W2 was 50.6, X2 was 1.85, plus W3, which was 280.5, times X3, which is 2.45, minus my PA, which is 102.9, times my lever arm distance here, which is 2.03, which represents H over 3 from the base of the retaining wall structure. And that's divided by W1 plus W2 plus W3. So 75.2 plus 50.6 plus 280.5. So I go through all of that and I calculate my distance D from the toe of the slope to be 1.57 meters. So what this is saying is that this distance D from the toe of my retaining wall structure to where this resultant force acts along the base of my retaining wall is a distance of 1.5, oh, sorry, you can't see that. From the toe of my retaining wall structure to where this resultant force acts is a distance D from the toe of the retaining wall structure. So this resultant force acts at a distance of 1.57 meters from the toe. So D is from here to here is 1.57 meters. So I need to compare this value of 1.57 that I've calculated to my middle third approach. So what my middle third approach tells me is that B over 3, where B represents sort of the width or the length of this retaining wall structure along its base. So the base of this retaining wall structure is 3.7 meters. So so B over 3, which is 3.7 over 3, has to be less than or equal to D, which is the value I calculated up here, which has to be less than or equal to 2/3 times B, and B represents 3.7. So if I go 3.7 over 3, that's 1.23 meters. And then I have to determine, is that less than or equal to 1.57? And is that less than or equal to 2.47? And if I go through and I do the comparison, yes, the middle third approach is satisfied because 1.23 is less than 1.57, which is less than 2.47. But say, for example, I calculated my D to be 0.9, then you would say your middle third approach wasn't satisfied because this criteria right here cannot be achieved. So if your middle third approach is achieved, your overturning criteria is acceptable. If your middle third approach isn't achieved, then your overturning criteria isn't considered acceptable. I'm going to pause and give you guys a few moments to look at this. And then ask questions. Okay, no questions. Okay, I think we're going to start to wrap this up. Here's a point to ponder. What do you think happens if there is poor water pressure? So say the material adjacent to the retaining wall structure isn't free draining. So say there was some poor water pressure. How do you think that impacts these calculations? Right. So pH would change because you would have to take that poor water pressure into account, and W3 would change in the sense of it changes, but not really, because think of it as a weight that is acting down on the base of your retaining wall structure. So is material that is saturated, does it weigh more or less than material that is not saturated?
More.
Right. So it weighs more. So the weight of it that's acting on the base of the retaining wall structure is more than what it would be if it was free draining. So you don't change the value of W3 in the sense that it then becomes a buoyant unit weight. It still remains as a saturated unit weight because it's a force acting downwards. But your PA value would change because you have to take that additional weight associated with your pore water pressure into account. So your PA value would become larger because you have that additional force from the water acting on your retaining wall structure. That's if it is saturated. So for this example here, Hong, because it was for free draining material, you use gamma bulk. But imagine if I gave you an example problem where I said water was at the ground surface. So if water is at the ground surface and your backfill material is considered saturated, then that's where these differences would arise. But in this example problem, most definitely, everything is in terms of gamma bulk. So that's some food for thought. I think I've talked a lot today. It's probably information overload. So I think I'll give you guys some time to digest this. Guaranteed there'll be an example or there will be a question like this on test number 4 as well. I know you guys will need some time to process it. Go over example problem, this one again, and go over example problem 1216. I'm happy to do sort of another class where you guys have had time to digest the material and answer any questions on the factor safety calculations for sliding or overturning. If you guys feel as a class that is something that would enhance your learning, I'm open to doing that. Because I present a lot of material, so it's a lot to absorb.
When would you hold it, on Wednesday?
Whatever is convenient with you guys. I guess you probably have tests, huh? Monday, Tuesday?
That's the only day we don't have an exam.
Okay. Does that work with you guys? Or I can do it Friday this week. Yes, I'll put a summary of what will be included and excluded. Yeah.
So Lena, we still need to understand that Rankine's chart kind of thing, right?
No, you don't need to understand it.
Oh, okay. Because for question 12.14, we use that. So that means we don't need to do 12.14.
No, you don't need to do 12.14.
What about 12.13?
12.13 is just, I think it's just the calculation using a rectangle. So it's just sort of an introduction to doing these factor of safety calculations for overturning and sliding. So it would be good to start with 12.13 because it's a fairly simplistic shape, and then you could progress to the more complex shapes. But 12.13 is fair game. 12.14 I wouldn't ask you on a test, and 12.15 and 16 are fair game.
Okay, thank you.
Would you guys prefer this Friday to have, say, a 1-hour session on factor safety calculations, or next Wednesday?
Oh, this
I think
Friday works.
Wednesday would be more helpful.
Wednesday works too. Doesn't matter.
Okay. I'll set something up. Okay. Sounds good. Okay.
And, do we need to go over the frost action chapters?
Yeah, read that on your own, but I'm going to send, what I'm going to do is I'm going to send you 6 questions to ponder, and one of those 6 will appear on your test, and not everyone will get the same question. So does that seem fair to you guys?
Sounds good.
So if you prepare for all 6, guaranteed you will get one of them. And there'll also be a course reflection question for each student as well.
So just one question from the last chapter.
Yes, just one question from frozen soils, correct. And it will be worth 2 marks. I am available to help with the FlowNet assignment. I have a meeting after class with another student, but this afternoon or tomorrow or Friday is fine. Well, I guess it's due Friday morning, so yes, I'll be available for a bit this afternoon and on Friday, or Thursday, sorry. So like usual, I'll send out my big long email. I'll indicate on Learn what is included and excluded on the test. I'll set up a review session. Maybe I'll do one Friday and one Wednesday. Those who want to come on Friday can come on Friday, and those that want to come on Wednesday can come on Wednesday.
And regarding duration, it's not going to be 1 hour, right? At least one hour and a half, right?
It won't be 1 hour. It'll be either 1 hour 15 or 1 hour and a half. You guys are pretty set on an hour and a half?
As other guys said, 2 hours would be great, but yeah.
No,
it's
you
up-
won't get 2 hours for this one. Definitely not 2 hours. I'm open to an hour and a half, but not 2 hours.
Sure, I tried.
I'm a stubborn lady. Ask my kids. But I'm flexible at the same time. Okay, I think you guys are probably spent. So thank you very much for joining me this morning, and thank you very much for being very understanding and cooperative in GM2 this year. I really appreciate your dedication and hard work. I know it's a lot of material to cover, and I know it's difficult material, but you guys have persevered and done really well, so I'm very proud of you. And hopefully you can retain some of the knowledge from this course, and you'll find it useful in your careers. So thank you very much. So I'll set something up for Wednesday and of next week and Friday of this week for you guys, and I'll send the and I'll put the links in Learn as well under our WebEx. Or actually, it might be easier if I just do my personal room. So I'll just do my personal room. Okay, have a great day, guys. And as usual, I'm always available to answer questions. So have a great afternoon.